Okay, so second part of 9.7 is working example 9.4. And this great problem it just includes so many neat things. And of course, as a student, when you hear an instructor say something like that, you're thinking, uh-oh, this is going to be hard. And it's really not hard. It's just getting the right equations in the right places. And so example 9.4 says that I have an ideal transformer, and everything that we've done up this point is, related to an ideal transformer. And it says I have an ideal transformer that has this 90 turns on the primary and the 2,250 turns on the secondary. It's connected to a 200 volt, 50 hertz source. Okay, so again, let me point out the obvious, that this and this have to be the same, right, in terms of magnitude. But we do want to remember this is an induced voltage, whereas this is a source voltage. Here's our polarity marks, and the sort of the same relationship of everything that we've looked at up to this point. Also, it says that the load across the secondary is drawing 2 amps. Okay, all of these are RMS or effective values. And he's going to include something that I hope we're remember, something called the power factor. And the power factor for this load, he says, is 80% lagging. Okay, and when you say lag, we're describing the current. So the current is lagging the voltage. Okay, so that tells us that this is inductive. Okay, so we've sort of set the stage here for this thing, and let's dig into it. Part A says, what is the effective value of the primary current? What is the effective value of the primary current? Now, I'm going to skip his initial solution where he does this reasoning thing, and we will reason, but I don't know if we're quite ready to reason at this stage, and it may be more beneficial to do this, okay, where we equate the two sides of this equation to each other, right? And instead of trying to reason it out, we're just going to plug in. So I know I have 90 turns on the primary, and I don't know what the current is. I have 2,250 turns on the secondary, and I do know the current there is 2 amps. So I solve this for I1, and I'm going to come out with 50 amps. Okay? Now, we should be able to reason that since this turns ratio, it's this relationship here, it's the voltage is 25 times greater on the secondary than it is on the primary. And the current, on the other hand, will have an inverse relationship where the current will be 25 times more than this current, and 25 times more than 2 is 50 amps, okay? So that's where that comes from. He goes through that determination in the first solution, where he does this, N1, N2, which is 90 over 2,250. I get 1 over 25. And so, I could use that, and I could say the current ratio is 25. And because the primary has fewer turns, the primary current is 25 times greater than the secondary. Okay, so that's one thing that I can do. And again, I apologize for this little quirk thing that's going on. I think I'm getting some intermittent internet here. So let me pause this and get this figure back up. Okay, part B in this problem says that what is the instantaneous current in the primary when the instantaneous current in the secondary is 100 milliamps. Okay. Well, again, this relationship is established. You know, this number 25, right? It's 25 times uh, the voltage, 25 times less the current. So if I'm saying that I have instantaneous current of 100 milliamps in the secondary, I'm going to have 25 times more that amount in the primary. You know, so that relationship is always there. So, you know, what he writes here, just, you know, he rewrites this as 0.1 amps. And so the primary current is going to be 25 times that, or 2.5 amps across there. Okay, that's simple enough. And that, you know, I think that's just, you know, basic understanding of how the transformer works. And then part C says, what is the peak flux linked by the secondary winding? What is the peak flux linked by the secondary winding? All right, well, again, we're saying this is an ideal transformer, so there is no leakage flux. But let me clean this slide up a little bit and we'll work through this. Okay, so solving equation 9.1 for peak flux. You know, we have this, and then knowing this relationship that the flux link in the secondary is the same as the flux link in the primary, I can use this and I can plug into this to get my value. Okay, here's a constant. The frequency in this one was 50 hertz, and the number of turns there was 90. Let's see if it's going to catch up. Yeah, it eventually catches up. And I come up with the peak flux as 10 milliwebers for this particular problem. All right, let me clean this up one more time and we'll do the last part of this. Might be a little bit the most challenging because of the use of the power factor, but we'll walk through it. Okay, so he says, you know, in this one, draw the phasor diagram. All right, so to draw the phasor diagram, the one thing that we don't have up to this point is what the voltage is for E2. We haven't had to calculate that, but we know the turns ratio, and we know 90 to 2,250. If we have 200 in, then we're going to have 25 times that on the output, excuse me, or 5,000 volts. Okay, 5,000 volts. So that allows me to put this value in here. Here is EG across here. And so I have E1 and EG are of course the same, even though one is derived and one is a source. So I've got that and that. So let me clear that up there a little bit. And then the thing that we are given, we're told that this current is 2 amps. Okay, so we know that I2 is 2 amps, and we also know that I1 and I2, they're going to be in phase with each other, right? And we talked about that, how the magnetomotive force, you know, has to you know, equalize each other from the secondary and the primary. Okay, and the only way that can happen is that the currents have to rise and fall with each other. And so, you know, I1 and I2 are in phase with each other. We've already determined that I1 is 50 times greater than I2, and that the voltage, you know, has the inverse relationship where it's like this. But what we're trying to do, and one other quick thing, notice that this flux always maintains that 90-degree relationship with the source, okay? And we talked about where that came from. But the one thing that we don't know is what is the angle of this current. And the only way we would know that is that we're given that the power factor is equal to 0.8. Okay, so it's given to us as 0.8. So you know, if we know that, and you know, we go back to some much earlier discussions of power factor, and I'll try to do include some remediation in this model in case you're cloudy on that. But you know, if I have 0.8, that's equal to the cosine of the angle between the voltage and the current. Okay, so that goes back to an old relationship. And if I go to my calculator and I put in, let's see, second inverse cosine 0.8, and I have this set up to display angle, I end up with 36.86. So I'm just going to put 36.87 degrees. Well, he rounds it to the tenths. 36.9 degrees would be the angle between the voltage and the current. And he told us it was lagging. Lagging always describes the current. So, you know, this shows that the current here is lagging the voltage by that angle given by the power factor. Let's see, did we get everything covered? Now that is what I would call a comprehensive type problem. Man, that covers everything that we've talked about, not only about transformers, but even going back to some much earlier work. Now, you've done the heavy lifting. The rest of this is pretty easy from now on. And we've just got a few sections that we tie up here, and we'll be done with this chapter. So, you know, make sure you understand this. I've got some problems I'm going to assign to you, you know, to go through some of this. But make sure that you've got this. If you didn't get it the first time, go back and look at it again, okay? And make sure that you know it.